Alright, in this lecture we're going to first summarize what we have found for the series RLC circuit, and then we will kind of generalize it by putting it into what we'll call a standard form, and we'll put that to use then in studying other RLC circuits, primarily the parallel RLC circuit. So let's review what we have found thus far. I'll draw our now familiar RLC circuit. We have a differential equation in the capacitor voltage, VC double dot plus R over L VC dot plus 1 over LC VC equal to VS. We found the roots. Well, let's first do this actually. Let's write the characteristic equation. Okay, this was the differential equation. Really comes from the equation of motion, or from KVL in this case. All right, our characteristic equation we found was S squared plus R over LS plus 1 over LC is equal to 0. The roots were then found to be S1 and S2 were equal to minus R over 2L plus or minus square root of R over 2L squared minus 1 over LC. We defined a term called alpha, which in this case is 1/2 R over L. Alpha, by the way, is called the attenuation factor. And we also defined omega n, which stands for natural frequency. Of course, this is angular frequency. It's also used or referred to as omega naught. That's what the book uses. So omega n or omega naught are the same quantity. And so therefore we can rewrite our characteristic equation as S squared plus 2 alpha S plus omega n squared. And the roots become S1 and S2 are equal to minus alpha plus or minus the square root of alpha squared minus omega n squared. Now we had to consider several cases. We had the case where alpha was greater than omega n, which would be the overdamped response. In that case, S1 and S2 were equal or real and distinct. So we had defined an alpha 1 as being equal to minus S1, which is alpha minus square root of alpha squared minus omega n squared, and we defined alpha 2 as minus S2, which was alpha plus square root of alpha squared minus omega n squared. And then we noted that alpha 2 is greater than alpha 1, which also can be shown to be greater than 0. And so our solution is, I would say complete solution actually, complete solution is Vc of t is equal to Vs, the driving constant, voltage plus a constant K1 e to the minus alpha 1 t plus K2 e to the minus alpha 2 t. And because alpha 2 is greater than alpha 1, we would say that this alpha 2 is going to decay more quickly. I'll draw it like this. This one will decay more slowly. Now it could be positive or negative. Not sure yet what the sign is. That depends on the initial conditions. But we can say that alpha, the second term, K2 times e to the minus alpha 2t will decay more quickly. So this is the case of the underdamped or overdamped response. All right, now we want to look at the case where alpha was less than omega n, which is the underdamped response. And here we have S1 and S2 are complex conjugates of each other. We're going to define a quantity, omega d. This is the dampened angular frequency. Define that as square root of omega n squared minus alpha squared. And therefore we have S1, S2 are equal to minus alpha plus or minus j omega d. And our complete solution is of the form Vc of t is equal to Vs plus, say, K3 e to the j omega dt plus K4 e to the minus j omega dt. Before, I think I used c and d for the constants. Oh, and then this is times e to the minus alpha t. All right, so this term decays, and the sum of the other two here are going to be some kind of sinusoidal. So this is one form, but we can equivalently write Vc of t is equal to Vs plus, say, K5 cosine omega dt plus K6 sine omega dt times e to the minus alpha t. That's a trigonometric form. Moving on to the next page, we could equivalently write Vc of t is equal to Vs plus K7 cosine omega dt plus theta, whole thing times e to the minus alpha t. Or, finally, we could equivalently write Vc of t is equal to Vs plus K8 sine omega dt plus phi, e to the minus alpha t. Now these constants, K1 through K8, are all related. Okay, they're not independent one from the other, and I'm not going to take the time to derive the relationship from one to the other, but it's just a bunch of trigonometry. The main point is that there are two unknown coefficients that will be found by satisfying two initial conditions. So we always have an initial condition, Vc at time 0, and IL at time 0. And so these together will lead to, let's say, I'm sorry, I should write up here, correct that, K3, right? Because K1 and K2 were related to the, when I was looking at the overdamped response. So K3 and K4, and then K5 and K6, and then K7 and K8. Those are all related. So satisfying initial capacitor voltage and initial inductor current will lead to K3 and K4, or K5 and K6, or K7 and K8, depending on which form you're going to make use of. And I think using the cosine, the trigonometric form of cosine and sine is a good choice. Although either of the other ones would do as well. The one you want to avoid generally is the first. Oh dear, I messed it up here. I'm sorry. I'm not paying attention. Okay. This is the complex exponential form. This is the one I would avoid. Okay. This one is the trig form, sine and cosine. That one's good. K7, and then it'd be theta, and K8 and phi. All right. These are fine as well. So let me try to correct my mistakes here. We have two initial conditions, capacitor voltage, inductor current, and those are used to find two unknown coefficients, either K3 and K4 for the complex exponential form, or K5 and K6 for a sine cosine trig form, or K7 and an angle theta for the cosine with phase form, or K8 and phi for the sine with phase form. So any of those will do. All right, lastly, we need to look at, or we will look at, we haven't looked at this yet, the case where omega n, is equal to alpha. This is the critically damped case. Critically damped case. Okay. And if we return to our differential equation, which we had put in a standard form on the previous page, we'd written s squared plus 2 alpha s plus omega n. I'm sorry, that's the characteristic equation. Yeah. I don't know if I said differential equation. This is the characteristic equation. That's what we want. Okay, so in the case where we have alpha equal to omega n, then we really have this characteristic equation, s squared plus 2 alpha s plus alpha squared, and that can be factored into s plus alpha squared. Right? So the roots then become minus alpha and minus alpha. So we have real repeated roots. And you might think, oh, okay, so the solution would then be of the form like VC of t is equal to Vs plus, and we'll have some initial, I'll say K10 e to the minus alpha t plus K11 e to the minus alpha t, right? Because I have alpha and alpha here, right? Of course, that's useless to write two terms. We might as well just written one term, K10 times e to the minus alpha t. It turns out in this case that the solution, indeed, e to the minus alpha t is a solution to that differential equation, but there's also another solution of a form that we have not yet encountered. And this you'll see over and over again. Eventually, when you have differential equations, this will become very familiar. But I'll just state it here, that if you have a repeated root, the first root is going to be the e to the minus alpha t, as you would expect. The second root will actually lead to a term of time t times e to the minus alpha t. And if you had a third repeated root, you'd have a t squared term and so forth. But we won't worry about that. So this is the form of our solution if we have critical damping. Now, as I mentioned before, this is a singular boundary point between underdamped and overdamped. And in any real circuit, we don't ever really encounter it, right? Because if you're just a hair to one side or the other, you actually have an overdamped or underdamped system. But I'm just stating it here so that you will at least have been exposed to it. All right, I'm now going to move on to the next page where we're going to look at standard differential equation form, which will serve us well when we look at a parallel RLC circuit. All right, so we want to put the differential equation for the RLC circuit, series RLC, into standard form. So we have previously defined alpha, omega n, and omega d. And we're going to use those in our differential equation. So we can write our differential equation in the following form. Okay, let me start off with what we had from the beginning, from the circuit analysis, from KVL. We had R over L here, VC dot plus 1 over LC is equal to Vs. Now, if we recognize that alpha, recall that alpha is 1/2 R over L, okay, and omega n is equal to 1 over square root of LC, then we can write the differential equation as V double dot plus 2 alpha V dot plus omega n squared is equal to Vs. Right? And notice that now, although our dependent variable V is interpreted as a voltage, we could put this into a very standard form of, say, x double dot plus 2 alpha x dot plus omega n squared equaled some x of s, okay? And so this is very general here. It could be electrical, it could be mechanical, it could be whatever. But we can already determine from here whether or not the system is going to be underdamped or overdamped simply by comparing alpha to omega n. So if the differential equation is placed into a standard form using alpha and omega n, then by inspection we can determine whether the system is under or over damped. Okay? So if I had, let's say I gave you an equation x double dot plus 6x dot plus 16, okay, equal 5. Question, is the system underdamped or overdamped? Well, we have omega n squared is equal to 16, therefore omega n is equal to 4. And 2 alpha is equal to 6, therefore alpha is equal to 3. And because alpha is less than omega n, therefore the system is underdamped. Just like that. And if we say, okay, what is the frequency that it oscillates? We have that as well. In fact, I can write the solution by inspection here. I can say the complete solution in this case, x of t, is going to be equal to 5. That's my forcing function, right? Plus, if I put it in the trigonometric form, I'll say some constant, what was I using, k? Let's check here. Okay, fine. Just use a and b, go back to that. A times cosine. Oh, I need to find one other thing. I need omega d, right? This is omega d plus b sine omega d, the dampened frequency. The whole thing is going to be e to the minus alpha, which I already know, alpha minus 3t. The only thing I'm missing is omega d. Omega d is the square root of omega n squared minus alpha squared. So that's 16 minus 9, which would be 7, square root of 7. So therefore, the solution is x of t is equal to 5 plus a cosine of square root of 7t plus b sine square root of 7 times t, the whole thing e to the minus 3t. And now I don't know, these are still unknown. I would have to, you would need to know x at time 0, and you would need to know effectively the derivative of x at time 0. Remember when we were doing capacitor and inductor, the capacitor voltage at time 0 was one initial condition, and then it turned out the initial condition on the current, I, was essentially C dV dt, so it was an initial condition effectively on the derivative of the capacitor voltage. And here we're speaking very generically, some variable x. I don't know if this represents a physical system or not. But once we had x at time 0 and the derivative of x at time 0, I could find a and b, and I'm done. Now, we also defined Z naught, the characteristic impedance. The characteristic impedance. And this has a practical use as well. In the above example I just worked, you were given the differential equation, right? And no circuit, no system, no resistance, no inductance, no capacitance, or if it was a mechanical system, you weren't given any mass and spring and damping coefficient and all that. You just were given this differential equation. So in that case, it was useful to put the differential equation into the standard form using alpha and omega n, and we could very quickly determine whether the system was underdamped or overdamped. If we're given a circuit, okay, so consider a circuit. We'll do a series RLC here, and let's say that I have 100 microhenry. Okay, that's 100 microhenry, and I have 4 microfarad. Okay, and I have 6 ohms. And the question is this system I'll put a voltage here, 5 volts. Is this system underdamped or overdamped? If I were to specify, for instance, this voltage at time 0 was 0, and let's let it go and see how it reaches 5 volts. Is it underdamped or overdamped? In this case, it's more expedient to use Z0. All right, Z0 is square root of L over C, which in this case is square root of 100 microhenry over 4 microfarad. So that's the square root of 25, or 5 ohms. All right. You don't know this yet, but the impedance has the units of ohms just like resistance does. Now, we had derived the relationship for underdamped, overdamped related to Z0 and R. I believe we did. Let me state it here. Or maybe I should rederive it. Yeah, let's just rederive it. I can't remember where I stated it before. So we have, if alpha is equal to omega n, this is critically damped, right? Critically damped. Okay, let me multiply both sides by L. Okay, I'm going to multiply L alpha is equal to L omega n. Let me go to the next page here. So I have L alpha equal to L omega n. Well, alpha is 1/2 of R over L, right? And omega n is 1 over square root of LC. So these L's cross out, and I get R is equal to 2 times, and I can stick this L inside the radical in the numerator, and I get square root of L over C. Or in other words, R is equal to 2Z0. And I'll actually call this R critical, right? Which means it's that resistance where the system is critically damped. Okay? So I can therefore say if R, this is for a series RLC, if R is greater than 2Z0, then it's overdamped. And if R is less than 2Z0, it's underdamped. So let's return to our circuit. We found, so for our example, we had R was equal to 6 ohms, and we found that Z0 was equal to 5 ohms. Therefore, we have 2Z0 is 10 ohms, and we'd say that R is less than 2Z0. So therefore, or maybe the better way to do it would just say R critical is equal to 2Z0, which is equal to 10 ohms. R is less than 10 ohms, is less than R critical. Therefore, system is underdamped. Okay, so conclusion. Okay, when given a differential equation, or even a characteristic equation, alpha and omega n can lead, or will lead, to a quick determination of whether or not the system is oscillatory. Okay, when given a circuit, if given a circuit, then use Z0 and R to determine the over-damped state, right, to determine whether or not it's going to oscillate.